Good day everyone, welcome back to my channel. Today we are looking at quadratic sequences, quadratic proofs, and you specifically determine the next three terms in the sequence with proof. Suppose you are given a sequence such as 2, 5, 10, 17, 26, and so forth. Now, I would like to actually expose you to one of the key principles relating to quadratic sequences, one of the principles that I actually discovered when I was still in varsity. So this principle is more prevalent in algebra or algebra 101 and your pre-calculus classes. So how this works is to actually devise a series of terms. In this case, we have A plus B plus C. This we denote as the first term or term 1. Equally or viably, you will have the second term now. In this case, we have 4A plus 2B plus C. That is our second term, term 2. We have third term, so we have 9A plus 3B plus C. That is our third term or T3. So for our logic and understanding of this insert, so I'll just devote this application to only having 3 terms. Now, we need to actually be able to understand how this concept actually works in mathematics, known as the footprint, or rather the shootprint method, is to actually subtract the term 1 from term 2, and equally so subtract term 2 from term 3. And how it works, so we're going to actually have our terms linked in this fashion. So we have term 2 and term 1 and term 3. So we know that there are silent ones here. So in algebra, we know there's a 1 there in front of the variable of A. Also have 1 there in front of the variable of B. And also 1 there in front of the variable of C. Similarly, we have 1 in front of C, the variable of in term 2. And equally that we have 1 there. So those are just some of the key understanding that one is to be able to denote and be able to actually understand and be able to apply them so that you can be able to execute this application successfully. Now, key in this application is to actually subtract term 1 from term 2. So let's go ahead and do that. So 4A subtract 1A, we have 3A. Okay. And then we have 2B subtract 1B, we just simply remain with B. And notice 1C subtract 1C, the C's will now fall off, so we don't have any value there that becomes 0. So we are done with the set. So we can just start placing that in one group, one set. So we're going to look at a second and third denomination in this case, term 2 and term 3, and we do that as well. So 9A subtract 4A gives us 5A. 3B subtract 2B just simply gives us 1B. So notice C gets eliminated as well, because 1C subtract 1C, we just simply remain with 0. So that's our second term of the first difference. This is our first difference. So remember now, since you're working with quadratic sequences, so we want to work with We want to find the second difference, D2. So now to do that, we're going to actually do the same application by subtracting 3A from 5B. So we have 5A subtract 3B gives us 2A, and then 1B. Notice there's another silent one here and another silent one there. I'm just doing this so that we are on par with this application. Okay, so now we have only 2A in this case. So this is our new set. So basically that's what we found there. Now technically what we do now is to actually note that this, in fact, this looks like a shoe print, hence the shoe print method. Now I need to actually explain the technicalities regarding this application. Is very of great importance and of essence, is to actually understand that one needs to be able to also find the difference of the sequence given to be able to apply the application into the into finding the missing variables in this case. So now what does this mean? I'm actually gonna need space. Let me just use this space here. So what this means, it means that if I'm given the sequence 2, 5, 10, 17, 26, and we are already told that it's a quadratic sequence, so we know that we have to work, or we expect to work with terms in terms of the difference. We have to work with second difference. So moving on, so to find the difference in this case, it will be 5 subtract, in fact, let's first find the first difference. 5 subtract 2 gives us 3. 10 subtract 5 gives us 5. 17 subtract 10 gives us 7. 26 subtract 17 gives us 9. Okay, let's check with the calculator. It's very important that one executes this successfully. Yes, it's indeed 9. So now that's our first difference. Our first difference. So this is our first difference, D1. So we know that we want to find our second difference since we are working with quadratic sequences here. So we subtract the values that we found in the first difference to find the second difference. So 5 subtract 3 gives us 2. 7 subtract 5 gives us 2. 9 subtract 7 gives us 2. So clearly we can see that the second difference in case of this application, our second difference is just simply 2. So now that 2 is very important. That's what we need. We need this 2. We need to equate that with our second difference. So remember, we're looking at the second difference. So we plug it there. So that's the 2 that I'm bringing forth there. Okay. So 2a is equals to 2. So we need to find the value of a. So we know that 2a is equals to 2. We need 2 times a is equals to 2. What value can I multiply by? 2 to give us 2. That's what it essentially means. To find that, we can just simply use algebra to do that. So notice I'm dividing by 2 on both sides because we have a coefficient of 2a. So if I cancel out the 2, I'll remain with a, and then 2 divided by 2 gives me 1. So in this case, I found a to be 1. So what I need to do now, I move on to the next difference now. The second, this difference here, remember I started off with that. Okay, so I need to take that now. So we have 3a this time, 3a plus, I'm talking about this difference, first difference now, plus 1b is equals to, this time, remember, I'm looking at this is the difference I'm talking about here. In this case, the value is 3. Okay, so we know that our a is just simply 1. We found it. There it is there. There it is. This is the value of a. So we plug it there. And then we have 3a plus b is equals to 3. So 3 times 1 gives us 3 plus b is equals to 3. b is equals to 3 minus 3. b is equals to 0. So this time, in this case, we know that b now is equals to 0. So now we need to now start looking at the initial series. Now there's the first term now, the very first initial difference that is given. So we now take that and plug it in. In fact, I'm going to need space, just a little bit of space here. Okay. So essentially now for the third insert we have a. Remember now I'm looking at this now, first initial set. So I have a plus b plus c is equals to, now that should be equated to the first initial value. In this case, the one leading value there is 2. So that is equals to 2. We know that we found a to be 1, plus we know b is equals to, remember a is equals to 1. There it is here. Okay, in the set here. And then b, we found it to be 0. It is there. So b is equals to 0. I'll just substitute that in there. Plus c is equals to 2. So 1 plus 0 just simply gives us 1, plus c is equals to 2. c is equals to 2 minus 1. c is equals to 1. So that is our value for c. Now what this means technically, it means that the original quadratic equation follows. Tn is equals to an squared plus bn plus c. That's the original quadratic equation. So now because we want to find the next 3 terms, so we can actually now start plugging in where a is, we plug in 1, where b is, we plug in 0, and where c is, we just simply plug in 1. Okay, so let's go ahead and do that. So we have Tn is equals to, so a in this case is 1n squared, b is just simply 0 multiplied by n, and then c is just simply plus 1. Tn is equals to n squared plus 1. That in itself is the general formula for our pattern. So we need to test it and verify, like in any science. Whenever you find a product or factors, or whenever you do any or carry any form of calculations, you need to test and verify whether the sequence follows. So very important for one to be able to understand that whenever you find or discover, or rather in this case, annotate a general formula, is to test and confirm your sequence or general formula in this case. So hence we need to test it and see. So let's test it. Now in this case, what I do now, I just simply get a space here so that I able to carry out the calculations. So remember now, we found the general formula. This is now a general formula to be Tn is equals to n squared plus 1. So let's see what happens if we need to find. So remember, we have term 1, term 2, term 3, term 4, term 5, term 6. So we want to find the sixth term is equals to, so we have to substitute in this case where n is, we substitute 6 and we raise that to the second power, plus 1, plus 1 here. So that's our general formula, following the general formula. So 6 times 6 gives us 36. So 36 plus 1 gives us 37. So term 6 is 37. So here we have, in other words, this pattern will follow 2, and when I need space, so what this means, the implication here is that the pattern, or this pattern, will follow the sequence. So remember, we start off with 2, 5, second term, third term, fourth term, 17. I'm looking at this here. And then fifth term is 26. So we need to find the sixth term, the seventh term, and the eighth term to address our question. So because they're asked to determine the next 3 terms in the sequence. Now, we already found the sixth term. So in this case, the sixth term is 37. So the seventh term also follow the same application. So we have Tn is equals to, remember there's a general formula, is equals to Tn is equals to n squared plus 1. So we want to find the seventh term this time. So where n is, we substitute 7. So we have 7 raised to the second power plus 1. So 7 times 7 gives us 49. So we have 49 plus 1 gives us 50. So the seventh term is 50. Okay, right. So let's look at, this is now the seventh term. Remember, we're looking at a seventh term. We've just looked at the seventh term now. Again, general formula, don't forget the general formula is Tn is equals to n squared plus 1. Eighth term now, so 8 raised to the second power plus 1. 8 times 8 gives us 64 plus 1 gives us 65. So that's eighth term. Eighth term is 65. And then that, in a nutshell, is the application relating to quadratic sequence with proof using the Shupran method. A very significant tool in solving quadratic sequences and determining different applications relating to quadratic functions. So thank you for watching. Please don't forget to like, share, and subscribe to my channel so that one is able to identify certain key pointers relating to these concepts presented. Don't forget to practice mathematics, enjoy mathematics, and have fun. Take care. Goodbye.